everybody. Welcome to the last and probably the best session of the entire conference. We are going to go on a journey today, a search for truth. I'll be your host, Rob Landers. I'm an engineering manager at FinDoc, where we focus on both sides of the payment experience, so we're a fintech company. Side note, we are hiring a PHP engineer who likes to build internal tooling, so if that interests you, please do apply. I've been writing software since I was 9 years old, almost every single day. I absolutely love software. I started in QBasic, and then moved on to C, and then C#, and eventually to PHP in 2012. So I missed all the PHP 4.x days, thank God. So we're here for a search of truth. And what is truth anyway? Well, people have spent entire lifetimes trying to figure out what truth means. And to define it is actually quite slippery. Even if you try to go into the dictionary, you will see that truth means the quality of being true. And so you say, okay, that's kind of obvious. What does true mean? And it says not false. And you go, well, if I look up false and it says not true, this is going to end really badly. But instead, it just says it's not real. So you keep going down the rabbit hole and eventually ending up at fact. Now, you can pretty much define fact as provably true. So we have basically a huge circle that a truth is that it can be proven true, which, yeah, it's a circle. And it's funny because humans, we can kind of navigate this ambiguity, even though we all disagree on what the details are. For example, what color is the sky? If you go and ask a random person on the street what color the sky is, they will probably tell you it's blue, even at night when the sky is very clearly black. So this is kind of cool, right? Like we can all disagree and agree that the sky is blue, even though it may not be blue where you are. And you can go to this URL here. I made a little thing with Mercure and PHP. And anyway, it'll update in real time, and we'll take a look and see what everybody says the sky is at the end of this. Well, like I said, humans can navigate this ambiguity well, but computers cannot. They are binary. They are either true or false. And this is where failure starts to creep into your system, because failure is absolutely inevitable. And sometimes failure isn't our fault. For example, there could be a flood or an earthquake or a toilet overflowing on the top floor, flooding the basement, which happens to have all the batteries and catches the entire data center on fire. True story. I'm not telling you who did that. Who did that? Anyway, you can't control everything. But we tried to build systems that are designed to fail. However, most of the time, failure is our fault. We miss something in a code review, we understand some requirements, we write a bug. It happens, right? I mean, that's just something that happens. But our goal is to prevent cascading failures, and this is usually caused by a whole bunch of little tiny mistakes. So for example, this code here. On the surface, it looks rather benign. And just a little background, in this system, a user either is an admin or is a customer. And true story, if they had just written if else, it would have caused an entire outage. However, a cache did not get evicted properly, meaning that a user became an admin and a customer at the same time. This ended up calling separate microservices, which put this system into an unknown state, which then tried to call in an infinite loop another service, which then crashed that service because it was an invalid state, and so it would retry and crash the next server running that code, and then it would retry and crash the next one, and the next one, until all the servers were dead. And everyone's wondering what's going on. Why are they dead? every time they came back up, they would get killed within a few milliseconds. So anyway, back to mixing up sources of truth, right? What is a source of truth? Well, we've already established that truth is basically a fact. So we could just stick a bucket of facts and we call that a source of truth, right? You reach into it and you grab a piece of truth. However, a fact has to be provable, right? So we need to stick a prover in front of it to prove that the facts are true. But we're software engineers and we don't like that. Naming is hard after all, so we call it a database and an application. So this is great. If you can stay like this forever, you should do it. Don't change this. This is perfect. Everything is great. But one day, I guarantee you, you'll all be sitting around getting ready for stand-up. The owner sticks his head into the room and says, guys, I am doing this huge marketing push next week, and the performance is just abysmal. It needs to be better. Can you guys fix it by Friday? Okay, thanks. Everybody looks around, and without fail, someone will suggest the end of the beginning, the cache. And everything will be fine. You will turn on Doctrine query caches, you'll turn on Doctrine second level cache, and it'll be great. But one day, someone is going to submit some code that looks kind of like this. And I'll give you a few seconds to see if you can work out what's wrong with it while I drink some water. How many people have spotted at least one thing? Just raise your hand. 2? Keep it up. 3? 4? If you saw 4, I want to know afterwards. So the first thing that's wrong with this is kind of subtle. And it's that the dependencies are not encoded in the cache key. So for instance, as you can see, our first line, we try to set a cache key of bookstore.revenue.year. And then inside the function, we get a store ID, meaning the first time it runs, for store ID 4, everything is fine. The second time we come to this code and it's store ID 12, we're gonna get store ID 4's stored cache. So we need to fix that. And that's actually pretty easy to do. We just put our dependencies into the cache key. Pretty simple. Now we fixed that bug, but we still have another bug. Well, maybe a bug, but essentially, we have no easy way to invalidate this cache. Basically, if you look, and we want to, say, update a store metadata, we have to go and loop through every single year and on that store in order to evict the cache key that is stored there. Secondly, if we, say, get more revenue in 2025, we also have to loop through all the affected stores and evict them. So we should introduce some cache groups, tags as they're called. And this allows us to basically say, hey, we updated the store, so we're going to be able to evict everything related to that store or all revenue related to that year. That's great, but there's still one more issue. And this one is so subtle that most people have no idea that it's even there. And that's that this cache set here has escaped our transaction. So, in other words, maybe just before this, we have set some, we storing that profit into the database. So we've recorded revenue. And then just after returning and setting the cache value, we divide by 0, run out of memory, who knows, and roll back our entire transaction. Now the user on the user interface is going to see a value that doesn't match reality. We're lying to the user, basically. And so now we need to talk about databases and transactions. See, a database is, well, a source of truth. And they come with defaults, such as, generally speaking, it's read committed. And what this means is that if we tell the database we want it to become orange, and then we have another transaction on the right here, going to the database to read it at the same time, in the transaction that set it to orange, it doesn't affect the other transaction until we commit. And it's only once we commit that the database turns orange. Thus, this code is effectively a form of cache pollution. And it can cause absolute havoc in your application because it causes your application to run code paths that it was not designed to run. And this can be benign at first, not really seeming to cause any kind of trouble, but it creeps into your database as well. Because maybe you read from the cache and store it in the database. Or you cause it to go down a code path that causes it to store something in the database that isn't true because your cache said it was true. There are many, many types of cache pollution that can affect your application. The one that we just saw was like a transactional cache pollution. So we have basically our values are able to escape the transaction. Another one is that we can also have key collisions. This is what we saw at the very beginning, the very first issue, where we had a key collision with another store. This generally can cause privacy issues, where you might leak information about other users. You can also forget to invalidate caches, which happens way more often than I think any of us would ever care to admit. So, we also have this other kind of cache pollution, which is called race to stale. And what this looks like is we have two transactions ongoing at the same time. On the left, we are going to update the database to orange. And we do that, and we evict that key from the cache. On the right, we request, what color is your database? It stores that in the cache and returns it. And then the transaction commits, and our database, is lying. Our cache, any request we make from that point on will tell us that our cache is blue. Our database is blue, but our database is orange. So now we're lying to our application, and this is almost very, very hard to reproduce. This is that kind of bug where someone says, hey, I'm seeing my cart after I have made a payment. Or, hey, I'm still seeing search results even though the inventory is 0. What's going on? That's how that can usually manifest. And it's pretty easy, or I should say easier said than done, to solve. Basically, we only want to write or invalidate a cache after we have committed the value to the database. And this basically means that you need a transaction-aware cache, which is pretty hard to build. I haven't really seen one that's good. So anyway, always, always, always encode your dependencies in the key. I cannot stress that enough because it's such a common thing to forget. Make it hard to invalidate your keys. Yeah. We need to make sure that your cache is only updated after we commit. And then, of course, the less obvious one is to actually just not even use a real cache. You can actually use Doctrine to provide a cache to your database, and it runs in the database, meaning when you commit your transaction, the cache gets updated. When it rolls back, your cache gets rolled back. And it's pretty simple to set up, actually. And last but not least, for the non-faint of heart, is to just change your transaction isolation level to read uncommitted. I recommend not doing this unless you absolutely know what you're doing. And it's really only here for completeness. but it actually is a realistic possibility. So you've got a stable and running application and it's doing fantastic. And then you're all sitting around about to have stand up and the owner pops his head in and says, guys, I signed up for this payment provider and I, signed us up for a thing. We're going to build an app. It's going to be awesome. And, we're going to make some serious money. I also want to send emails and notifications and all of this. And then he leaves and everybody looks at everybody and okay, cool. That sounds fun. So we have our app and we build our API and we have our database. Oh yeah, we also have a cache. And by the way, your app also probably has a cache. That makes it even more fun, but we're not going to go into that. But now you have a new source of truth in your system, an external system. The thing about external systems being a source of truth is that they are not part of your transactions. And sometimes the side effects might be permanent. If you send an email, you can't unsend it. Ask all the people who have sent 1 o'clock emails. Everybody wishes you could unsend an email, and it's 30 years later, it still hasn't been invented. Secondly, the changes might actually be visible because it is not part of your transaction. So if you're running a long payment batch process in the middle of the night, there's probably a user who's going to log in to see why their payment failed, and they're not going to see any record of it because you haven't committed yet during your batch process. I'm not going to go into why you're doing that, but it happens. So there's something to be aware of when you have external systems, but there are lots of good solutions out there. One is to use the outbox pattern with Messenger by using Doctrine to be your messenger provider. This is also pretty easy to set up. And here's the thing, if it fails, then you can just roll back the whole transaction, which rolls back the messages, meaning they never go anywhere. And one thing that you have to take into mind too when you're using Messenger is that it basically promises you at least once, meaning it can run the same thing more than once. And dealing with that, we use something called idempotency keys. This is something that most payment providers provide out of the box for free. Some of the really good email providers out there do the same thing. And this basically allows you to encode something into the request where the first time you send it, it actually performs the side effect. And the second time that you send it, it just returns to you the same thing it sent you the first time. Meaning if your messenger does happen to pick up the same message twice, the side effect only happens once. So what do I mean when I say using the outbox pattern, for instance? So what you want to do, effectively, is just take your message, before you send your message, write to the database, hey, I'm about to send this message, or I'm about to perform this side effect into your database. Once it commits, it'll get picked up by Messenger, and Messenger will then update that record as either success or failed. And if it happens to roll back, and you're using idempotency keys, probably using the same ID that you have in your record as your idempotency key, then you can guarantee you basically only perform the side effect once, even if it rolls back. Last but not least are compensating actions. Compensating actions are ways to roll back a transaction by rolling forward. So, in other words, a good way to think of it is if you take someone's money and you want to undo that, you just give them back their money, aka a refund. That would be an example of a compensating action. And if you really, really, really want to go all of the way, you could just not use transactions. That's a joke, though. Don't do that. Or maybe not. So, everybody is happy. We're making money. Everything is going great. And then, one day, you're all sitting around, about to start your stand-up, and the owner sticks his head in, and he says, Guys, I just got some investor money. We are going to scale to infinity and beyond. It's going to be awesome. I'm going to my yacht. See you guys later. Everybody looks at everybody and says, did he just write us a blank check to build whatever we wanted? And so, yeah, we have our amazing system and it's running super stable. We haven't had any issues in a while and everything's going great. So we all sit around and we all try to figure out, okay, how can we scale to infinity? How can we do that? And lo and behold, someone will inevitably suggest, let's shard the database. And that seems like a pretty good idea. So you do it. And now you have many, many sources of truth in your application. And you've got a whole new set of problems. One, there's no more transactions. It's just not possible unless you pay someone a lot of money to be able to do that. But, you're all engineers. You're going to make it happen. There's no more joins anymore. That's gone. Poof. You can't join across multiple databases. You're denormalizing data across shards so that you can do joins, but that is hard too. Migrations become a nightmare. I work somewhere with over 1 billion shards. Yes, B with 1 billion. And migrations were literally a nightmare. It took a long time, and you had to have your code be able to handle both sets of migrations for that entire period. In order to move data between shards, you basically need a PhD to even explain it. And cache keys also need to be updated to include the shard IDs. And then you have to build this whole side infrastructure in order to search your data effectively. And then no one knows when now is anymore. If you ask the database when now is, every shard will tell you something different. Whoops. So I would recommend not doing this, at least for quite a while. Because here's the thing. You can go back to that original design and go for quite a while. And this is because truth is meant to be built. We design it. We engineer the truth. We engineer the prover that sits in front of the bin of facts. Truth is whatever we build it to be. So I hope that with careful design, we can keep our caches sufficient and consistent. We can keep our side effects reliable and our systems trustworthy even as they grow. So when failure inevitably happens, we'll be ready. That was a lot shorter than I thought. Thank you for coming to the talk, and I hope you have a pleasant weekend.